Hello and welcome to this video. We are solving the exercises of chapter 3 from the book Contemporary Abstract Algebra 10th edition by Joseph A. Gallian. In this video we will solve the exercise 20 and exercise 21. Okay. We start with the exercise 20. The statement is, let G be a group and n is any odd positive integer with the property that xn is equal to identity for all x belongs to G, and if a and b belongs to G and a square is equal to b, then we have to prove that a is equal to b. Okay. Since n is an odd integer, this means n is of the form 2k plus 1, and also xn is equal to identity for all x belongs to G. Now let a and b belongs to G such that a square is equal to b square. Okay. Since a and b belongs to G, this means a to raised power n is equal to identity and b to raised power n is equal to identity, because these conditions hold for all elements of G. And since n is equal to 2k plus 1, so a, instead of this, a to raised power 2k plus 1 is equal to identity, and we can write it as a to raised power 2k into a is equal to identity, and in this way we can see that a inverse will be equal to a to raised power 2k. Similarly, b inverse is equal to b to raised power 2k. Okay. Now consider, or since a square is equal to b square, if we take the power k on both sides, we will get a to raised power 2k and is equal to b to raised power 2k. But we know that a to raised power 2k is a inverse and b to raised power 2k is b inverse. So we can write it as a inverse is equal to b inverse. Taking inverse on both sides, we got a is equal to b, and that is what we want to prove. Okay. The next question is, the question 21 is a tricky question. The statement is that for each divisor k is greater than 1 of n is an integer and k is its any divisor, ukn is the subgroup of unitary group under multiplication modulo n, and it is consists of all those elements of unitary group which are congruent to 1 mod k. For example, in the unitary group under multiplication modulo 21, U321 consists of elements 1, 4, 10, 13, 16 and 19, because whenever we will divide this 1, 4, 10, 13, 16 and 19 with 3, we will get the remainder 1. Similarly, the subset of unitary group U721 under multiplication modulo 1 is 1 and 8. Only these two elements give the remainder 1 when divided by 7. Okay. Now the question is, list the elements U420, U520, U530 and U1030. And the last part of this question is, prove that UKN is a subgroup of unitary group under multiplication modulo n. First of all, we list all the elements of unitary group U20. Unitary group U20 has the elements 1, 3, 7, 9, 11, 13, 17 and 19. These are those integers which are less than 20 and are relatively prime to 20. Okay. This form a group under multiplication modulo 20, with 1 is the identity element. Now we have to find U420. Okay. Because this 1 is congruent to 1 mod 4, so this 1 belongs to this. But this 3 is not congruent to 1 mod 4, so 3 cannot belong to this group. And similarly 7 is congruent to 3 mod 4, means 7 is not congruent to 1 mod 4, therefore 7 also does not belong to this group. But we can see that 9 is congruent to 1 mod 4, so 9 will belong to this group. Similarly, we will check one by one every element and we will get this group 13 and 17. So this group subgroup consists of, okay, if we will prove later that this is subgroup. So this set consists of 4 elements. Now U520. Now we will check everything for modulo 5. 1 is of course congruent to 1 mod 5. So 1 will belong to this group. And similarly, if we see 11 is the other element, 11 is congruent to 1 mod 5. So 11 also belongs to this subset, and none of the other element will belong to this group or this set. Okay, we move to the unitary group under multiplication modulo 30, and this group consists of the elements 1, 7, 11, 13, 17, 19, 23 and 29. And we have to list the elements of the set U530. We have to find those elements which give remainder 1 when we divide it with 5, and that is also 1 and 11. No other element give remainder 1 when it is divided by 5. And similarly, U1030 is also the same set 1 and 11, because no other element give the remainder 1 when divided by 5, or we can say that divided by 10. Alright. Now the last part of this question is, now we have to show, or we have to prove that UKN is subgroup of UN for all divisors K greater than 1 of n. Okay. Now clearly the identity 1, which belongs to unitary group under multiplication modulo n, is 1 is congruent to 1 mod k for any k. This means the identity element 1 must belongs to UKN. Okay. We move to the next. Okay. Let A and B belongs to UKN. We have to show that this set is closed under multiplication modulo n. if A and B belong to this set, this means A is congruent to 1 mod k and also B is congruent to 1 mod k. And if A is congruent to 1 mod k, this means there must exist R such that A is equal to 1 plus kr, and similarly if B is congruent to 1 mod k, then there must exist an integer s such that B is equal to 1 plus ks. Alright. Now consider A, B, and it will be 1 plus kr into 1 plus ks, and that will be equal to 1 plus ks plus kr plus k square rs. And if we take mod k, then AB is congruent to 1 mod k, because all these three terms are multiple of k, so they will vanish. And since the product of AB is also congruent to 1 mod k, this means AB belongs to the set UKN. This means so far we have proved two axioms of group, that is identity element and the closure for this set UKN, and we know that the associative law holds in all the subsequent subsets of a larger set if it holds in the larger set. So we know that the associative law holds in the unitary group modulo n under multiplication modulo n, so it will hold in all the subsets of associative law holds in U, K and N. Now the only axiom which is remaining is inverse. So let A belongs to UN. This means we have to show that A inverse also belongs to UN. We need to show. And if we want to show that A inverse belongs to this, UK, we have to show this is also UK. We have to show that A inverse is also congruent to 1 mod k. Now since A belongs to this, so A will be congruent to 1 mod k, and this means that A is equal to 1 plus k r. Let A inverse is equal to t. We multiply A and t. We will get A and t, because it is inverse of each other, so we will get the identity element 1. And this means AT is congruent to 1 mod k. And now since A is congruent to 1 mod k and AT is congruent to 1 mod k, this means T is congruent to 1 mod k, and T is actually A inverse is congruent to 1 mod k, and this means A inverse also belongs to U, K, N, and hence UKN is subgroup of UN for any k divisor of k. That's all about this lecture. See you next time.